Look at this. Recording is working. Great. All right, so let's try again. I'm going to share my screen. Very good. Okay, so I just wanted to go back and review a few things from last time. There are a couple of important quantities that were discussed last time, and I've shown here an example, UPS, ultraviolet photoelectron spectrum of gold, and the corresponding diagram for the excitation process on the left. So here we're taking the X-ray and exciting an electron from the valence band of gold, which is then being photo-emitted. The energy of that electron ends up being greater than vacuum, and the extent to which it's greater than vacuum gives the value of the kinetic energy. And when you look at one of these spectra, what you'll see is that all of the various electrons that can be promoted from the valence band into vacuum, and the spread in energy there allows you to measure the bandwidth, and you can see some peak shape in there that tells you something about how the orbitals distribute within gold, and this would be some combination of S and D functions that are filled. There's this background signal that comes from scattered electrons. Remember that electrons scatter very effectively, much more so than photons do, and so you create a photo emission or a photoexcited electron, and it often collides with another charge in the crystal or an atom in the crystal before escaping, and that deposits some energy in the crystal, and some of those electrons continue out of the crystal and escape, others do not. And so the ones that do escape after a collision give you a apparently much more tightly bound electron. So you're paying extra energy to the crystal before the electron escapes, and that makes the binding energy of the scattered electrons larger, and it contributes this background of photo-emitted electrons that have scattered off of the crystal on their way out. And then as you go deeper and deeper into the electronic structure, or to higher and higher binding energies, eventually the electrons hit zero kinetic energy. They no longer escape. And that cutoff there, that's the most tightly bound electron that can be emitted from the sample. And you measure the width from the onset, which is the Fermi energy, all the way down to this cutoff, that 16 eV wide collection of photoelectrons, when subtracted from the photon energy, gives you the minimum payment that you must make to escape the crystal, which is equal to the work function of the material. Okay, so couple of different quantities hiding in there. You'll hear a lot about work functions if you go to talks about devices. And that work function is kind of an intrinsic measure of the Fermi energy relative to vacuum, and tells you how reducing a material is. We talked about how different materials have different Fermi or different work functions, and that sometimes a surface adsorbate influences the work function. So some materials have a range of work functions depending upon how their surfaces are functionalized. We also talked about X-ray emission as a probe of the band structure and the types of orbitals in the band. So there are two X-ray fluorescence spectra shown on the left. Those were generated by creating whole states in the 1s core orbital in one case, and in the 2p core orbitals in the other case. And recombination of that core whole with a valence band electron gives you an X-ray. Now, remember that selection rules really matter here. There's very little charge transfer character to these because of the poor overlap. So the selection rules apply in force, and that means that the peak intensity tells you about the symmetry of the transition, You have to do plus or minus 1 in the orbital angular momentum. So if you create a 1s hole, the recombination has got to come from a p orbital wave, a wave function that has p orbital symmetry. And so on the top, the big intense band at the highest fluorescence energies, which is the top of the valence band, that band is really p orbital derived. And at the bottom of the valence band, or the lowest X-ray fluorescence energies, you see s orbital derived transitions. And that tells you about how the p's and the s's within the bonding orbitals of the silicon lattice distribute in energy. And I find that really cool. It's a very interesting probe of bonding in solids. All right, so today we're going to talk a little bit more about bonding in solids, and we are going to look again at molecular orbitals here. So I showed you some of these figures last time. We're going to go a little bit deeper this time. Why are you? That's sort of annoying. Okay, so I've shown two MO diagrams here for dihydrogen and trihydrogen, sort of a fictitious molecule. And what we're doing then is taking hydrogen 1s functions and making linear combinations of them. The linear combinations allow you to deduce the molecular orbitals. And you're familiar with the constructive interference of those two hydrogen 1s orbitals giving you the sigma, the destructive interference of those two orbitals giving you the sigma star. And you get wave functions, psi 0 and psi 1. There's a typo here. The bottom one should be the 1s function for hydrogen A plus the 1s function for hydrogen B. And psi 1, the antibonding orbital, should be A minus B. Now, an important energetic quantity, beta, this is a measurement of the orbital interaction strength and the spread in energy of the bonding and the antibonding levels relative to the parent orbital energy, which is labeled E alpha, is equal to beta. So beta is the orbital interaction energy, alpha is the parent orbital energy. And so you can express the bonding and antibonding combinations as alpha plus beta and alpha minus beta. Now you go down to trihydrogen, and again, the lowest energy combination is what we call the totally symmetric combination, or the all constructively interfering combination of hydrogen 1s orbitals. So they all have the same sign, and you get a linear combination that is the sum of each of those orbital functions. And as you go up in energy, you add nodes. So the very highest one, of course, is going to be the totally destructively interfering combination, where there's a node in between each hydrogen orbital. And then the one in the middle has a single node, and that single node falls on the central hydrogen atom. So there's an electron missing from my molecular orbital diagram on the left there. Trihydrogen, of course, would have 3 electrons in total. And so the highest occupied orbital would be this central orbital, which is a non-bonding orbital. And you can see again beta shown there on the left. The all bonding combination is E minus, alpha minus beta, and the anti-bonding combination is alpha plus beta. And so you can see that trihydrogen is not a very strongly bound fragment, because that extra hydrogen does not contribute a lot to the energies of stabilization relative to just E alpha. Anyway, the most important thing is that the linear combination here, as you go from bottom to top, increases the number of nodes. The lowest energy one is the totally symmetric combination, and the highest energy one is the totally anti-symmetric or totally anti-bonding combination. And this middle one here is non-bonding, or approximately non-bonding. Okay, so Let's take a look at aromatic hydrocarbons. Those present a really nice example of this kind of thing. See if I can make my, I don't know why you want to do that. There we are. Okay, so aromatic hydrocarbons are really nice demonstration functions for how MOs build up. I've shown the MO diagram on the right for benzene, and the various SALCs, or symmetry adapted linear combinations of the p orbital functions in benzene. You could think about this as just a ring of hydrogen 1s orbitals if you wanted. But remember that each one of those lobes you're looking at there on the right is just the top of a p orbital function with pi symmetry that makes up the aromatic resonant portion of the benzene molecule. So at the very bottom, you see the totally symmetric combination, and as you go up in energy, you see increasing number of nodes. There's another typo here. The top orbital should have 3 nodes dividing all of the atoms. So none of those interactions are constructive interactions. They're all destructively interfering p orbitals, so totally pi star. Notice the betas labeled on the diagram here are still 1 beta for the HOMO relative to E alpha, and 2 beta for this totally anti-bond or totally bonding combination down there on the bottom. Now, physical organic chemists teach this thing called the Frost circle. The Frost circle is a very simple way to put together a molecular orbital diagram and the relative energy spacings and the degeneracies of aromatic molecules. So if you just take a circle and then you draw the shape of the ring inside of that circle with the point of the ring facing downward, you end up with something that estimates the orbital spacing. So if you write an orbital at each one of the points on the ring, which I've done over here on the right, you can recover the energy level spacing and the degeneracy. So the bottom of the ring is a single point or a single MO. The next 2 atoms make 2 MOs. The next 2 atoms make 2 MOs. And then finally, this atom makes 1 molecular orbital. And the energy spacings of those functions are shown: -2 beta, 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 and +2 beta. All right, so these energies actually come from Huckel molecular orbitals theory, and it has this 2 beta cosine 2 pi I over n. This is a n is an index, and I is an index, and n is the number of atoms in the ring. But I'm just putting it up here to show you that it varies as a cosine function, and that's why this Frost circle trick kind of works. So you can calculate the energy spacings using this equation, and we're going to do that in a little more depth here in a few slides. But remember, all bonding on the bottom, all anti-bonding at the top, and intermediate levels of bonding as you go from the bottom to the top. 1 node, 2 nodes, 3 nodes. And so if you use that idea, and the totally symmetric, and then building up number of nodes, you can write out MO diagrams pretty easily for highly symmetric systems like this. So let's take a look at a series of different rings making linear combinations of their p orbitals here. Of course, we start with ethylene. Ethylene has just pi and pi star symmetry orbitals, spaced in energy about E alpha. Cyclopropenium cation, or a cyclopropene ring with a bunch of p orbitals here. With the point down, you have the totally symmetric, and then this pair of orbitals with a single node going through them. Cyclobutadiene in its symmetric form with the point facing down gives you this totally symmetric combination, and this pair with a single node. Notice these nodes now change from horizontal to vertical, so the 2 degenerate sets the nodal structure just gets rotated by 90 degrees. And then again, you see the same kind of thing here with cyclopentadienide, or a 5-membered ring with 5 p orbitals, totally symmetric, one node, 2 different orientations. This one's horizontal, this one's vertical. Now, 2 nodes, we have a node here and a node here, and then we have a node there and a node there, and those 2 pairs of nodes are now rotated by 45 degrees. And then we go to benzene, and you get the structure that I showed you before. 1 node, 2 nodes, these guys rotated by 30 degrees, and 3 nodes rotated again by 30 degrees. So it's pretty simple. You know, it's just the number of possible combinations, increasing numbers of nodes as you go up. And this process continues all the way, until you have an infinitely large ring of these p orbitals. So at the bottom, totally symmetric; at the top, totally antisymmetric, and you get doubly degenerate molecular orbitals as you go up and up and up, and nodes that are rotating in smaller and smaller increments. As the number of p orbitals in the chain increases, and eventually you get a band of orbitals that have no spacing, or effectively no spacing between levels. So you can see how this sort of simple picture for making these linear combinations translates in these various ring systems to an infinitely large combination of orbital functions, which is what you need to do to understand the symmetry of a solid. So let's see here. I'm going to just make sure I can see. I want to be able to see the chat function just in case somebody has anything that they want to be able to say. Yeah, there's also this raise hand thing, but I haven't quite figured that out. Anyhow, so I'll put this chat down here in case you want to ask a question. All right, or just interrupt. Even better, just interrupt. All right, so let's take a look at this process in a little bit more formal kind of a fashion. So you can derive these kinds of band structures and all of these different wave functions using something called a block function. This is just a physicist, a mathematician's way of doing this in a kind of automated fashion, and it's, all of these aromatic hydrocarbons, these ring systems obey this kind of a method of generating MOs. So let's talk about a linear chain of hydrogen atoms. You could think about a linear chain of p orbitals that are a pi symmetry if you wanted. And I've just drawn out 5 different hydrogen atoms here. And I've given each one of them a number. So hydrogen 0, 1, 2, 3, 4. And then I've defined a spacing between those atoms as A here. And you should think about each one of those atoms as having a hydrogen 1s orbital wave function, which is labeled here as chi n. So this would be chi 0, chi 1, chi 2, chi 3, chi 4. And so you've got this system of hydrogen 1s functions evenly spaced with a distance of A repeating. And so if you have a system like this in a ring, then you can use a block function to generate any linear combination of those component orbitals chi 0 through chi n. A block function is shown here on the right. So the wave function of interest now, we've given it a index of k here, which we're going to talk a lot about. So psi of k is just a linear combination of component orbitals chi n multiplied by this function e to the I k na, where a is the separation and n is the number of the component orbital. So you can just take this function, and for each one of those hydrogen 1s orbitals, 0, 1, 2, 3, 4, calculate this quantity, and then add them together, and that will give you linear combinations. Now, it helps to know that e to the I kx is equal to this cosine kx plus I sine kx. That piece of this equation has this periodically varying function here. And so, remember that this is defined for a ring of hydrogen atoms, which when infinitely large, of course, is essentially linear. And it has this periodic cyclical kind of a expression. Okay, so block functions very periodically generate linear combinations in a very straightforward manner. And this quantity k defines wave functions with different degrees of periodicity, as we're going to see here in just a second. So let's take a look at two solutions for this thing. We're going to do k equals 0 and k equals pi over a. All right, and we'll explain why those two solutions are of interest in just a minute. You can just quickly look at the diagram here of the various orbital symmetries and see that the solution k equals 0 is the totally symmetric combination of hydrogen 1s functions, and the solution for k equals pi over a is the totally antisymmetric one. Okay, so let's look at how the block function generates those different wave functions for you. So psi of k, now where k equals 0, is shown here. So it's the linear combination of each of these different hydrogen 1s functions, and we've just taken out this IKA and stuck in a 0 because we're solving for k equals 0, so the rest of the components up there doesn't matter. E to the 0 is 1, and so the linear combination of all those chi-n's is just the sum. So chi0 plus chi1 plus chi2 plus chi3 plus chi4. So k equals 0. When you stick 0 in the exponent of this block function here, converts this e to the ikna to just e to the 0, and you're just taking the sum of each one of those functions. So now let's do e to the I, where k is equal to pi over a. All right, so you take this pi over a and you stick it into the exponent, which I should have included here, has an a in it. So pi over a, we're going to just cancel the a's and stick a pi in there for k. So now we have e to the I pi n. And e to the I pi n is also relatively easily solved because e to the I pi is equal to -1. So this is a consequence of the cosines and sines that were shown on the previous page, or you can just remember that e to the I pi is equal to -1. So now you have the sum of -1 raised to n times chi n. And so if you do the linear combination of each of those and you stick in a 0 and you stick in a 1, you stick in a 2, a 3, and a 4, you'll see that it varies from plus and minus to plus and minus across the linear combination. So for example, we'll stick 1 in to this summation. -1 raised to the first power is -1 times chi1, so that gives you minus chi1. Let's stick in 2 into n there. -2 squared is +1 times chi2 gives you plus chi2, and so on and so forth. So 0 and pi over a happen to be sort of simple solutions to this block function. When k equals 0, the wave function is totally symmetric, and when k equals pi over a, you get a node between each of the orbital functions.
Can I ask a question?
Yes.
The psi 0 at the bottom, would it be psi of a over pi over a?
Yes, it should be pi over a.
Oh, okay.
Another typo. I should have brought paper to take notes on these things. If you see a typo on the slide and you stick it into this chat window, I can go back and recover these things at the end and actually improve my slides. So I would greatly appreciate it, and I will be giving you extra credit for doing that for me. So please, if you notice a typo, go ahead and type it in there, and that will help me improve the slides before I upload them, for example. Um, so, all right, does anybody else want to ask a question about this? All right. So now let's take a look at what happens in between. So we've solved this thing for k equals 0 and k equals pi over a. Let's take a look at what happens in between, and also let's take a look at the energy of each of those functions. Okay, so I've plotted here on the left your first energy versus momentum diagram. All right, where this is energy versus the index k. Okay, and remember that the solution where k equals 0 is the all bonding combination. And in a ring, this all bonding combination has the energy alpha minus 2 beta. And the solution k equals pi over a is the all anti-bonding solution. And it has energy of alpha plus 2 beta. Okay, so you can remember that from this example here of benzene, alpha minus 2 beta, alpha minus beta, alpha plus 2 beta. As you go up in energy from the all bonding to the all anti-bonding case, you traverse 4 beta in energy. Okay, so each of the various molecular orbitals in a ring, or in an infinitely large ring, has a different value of k, and you go up in energy from alpha minus 2 beta toward alpha plus 2 beta in this fashion shown there on the left. Okay, so this energy is the same as the energy that I talked about for the Frost circle. It has this functional form of alpha plus 2 beta cosine Ka. And so for any given value of k, you can calculate an energy, or you can just plot this cosine function over here on the left. Okay, so as you traverse the various values of k from 0 to pi over a, the energy of the of this function varies like cosine. Now, what you'll find is that the only values that are actually unique in this thing are minus pi over a to pi over a. Okay, if you go beyond that to higher value, let's say 4 pi over a, you end up just cycling back, and it just oscillates. And so really the only unique values are in this range of minus pi over a to pi over a. And people call this unique range of values a Brillouin zone. And we're going to look at Brillouin zones here in a few slides that are a little bit more complicated than this. But just remember that these are the only unique solutions. The only unique wave functions have k values that fit into that range. Okay, so you can see the energies of all of these different wave functions here oscillating in this fashion that goes as cosine of k from 0 to pi over a, and you get this spread in energy of 2 beta, just like you would for any aromatic system. All right, so let's talk a little bit more about what k is, okay? Because k is used to talk about wave functions. It's kind of like a quantum number in solid state physics. K, the value of k tells you about how many nodes there are in a wave function. It also tells you something about the symmetry of that orbital. So we have these two solutions for k equals 0 and k equals pi over a, and the k equals 0 one has no nodes, right? the k equals pi over a one has many nodes. So the value of k, the way I think about it is like the degree to which the orbital is antibonding or bonding. It's kind of like a wavelength. Okay, so it's a measure of the how periodic that function is, how rapidly it oscillates through the lattice. And so you can think about the wavelength of the molecular orbital wave function being described by this value of k. So for these hydrogen 1s orbitals, as k approaches 0 in an infinitely large ring, the wavelength of the electron in that MO, in the MOs, becomes infinitely long, right? So as you approach 0, the number of nodes goes to 0, and you end up with this very long wavelength. As you go towards pi over a, what does the wavelength become? Well, it becomes 2a, right? So the wavelength would be defined as the, say, the peak to peak distance, which is 2 unit cells in this example. And so the wavelength of this wave function, pi over a down here, is the separation between, say, chi1 and chi3, or chi0 and chi2. That value of 2a is the wavelength of this wave function. So the k tells you how rapidly the wave function oscillates. It tells you about the wavelength of that wave function. And because of that, you can think about it in terms of the momentum of the electron. If you remember de Broglie's relationship. So, the connection between the classical and the quantum mechanical here is that wavelength and momentum are connected by h. So they're inversely related by h. And so this k is really a measure of momentum. You can think about the lambda and the k being related by 2 pi, right? And so the k and the momentum are proportional to each other. So, k is a measure of how rapidly the wavelength oscillates. It's a measure of the electron's momentum in a classical kind of a sense. So physicists talk about this value of k as a quantum number for a given wave function. And we're going to see a little bit more about how that's useful in just a moment. But just to help to drive this thing home a little bit and review kind of how this connects to band theory, let's remember what determines the width of a band for a moment. So you've seen here from this alpha plus cosine beta that the width of these orbitals, of these infinitely large circles of hydrogen 1s orbitals, is 4 beta. And if you think about what determines that spread in energy, it's all about the magnitude of beta. Okay, and beta is this orbital interaction energy that falls out of Huckel theory. I've shown you how that spread of 4 beta now changes as you vary the unit cell dimension. Okay, so if you have a chain of hydrogen 1s orbitals that are 3 angstroms apart versus 2 angstroms apart versus 1 angstrom apart, as you go from left to right here, the 3 angstrom separation means that those hydrogens do not interact very strongly at all, and beta is not worth very much. And as you push the hydrogen 1s orbitals together, you can see beta getting larger, and the spread in energy as you go from k equals 0 to k equals pi over a getting larger. So what you're saying here, as you push the hydrogen 1s's together, is that beta is growing, and the totally symmetric combination, the all bonding combination, drops in energy, and the all anti-bonding combination increases in energy. So, you know, just to connect these two pictures, the width of the band is all about orbital overlap. And in energy units, this is all about beta changing. Okay, so the interaction strength goes up, beta gets larger, and this diagram, this energy versus K diagram, gets wider and wider. All right, so let's do this process again, but this time we're going to do it for p orbitals instead of s orbitals. Okay, so we're going to talk about k equals 0 and k equals pi over a again. Those are the limits of the Brillouin zone, right? All the other quantities of interest fall in between 0 and pi over a. So k equals 0, that solution is still a summation of all those p orbitals. But now, if you take those component functions here and you line them up to make sigma bonding interactions, if the symmetry of the orbital is unchanged, as you go from 0 to 1 to 2 to 3 to 4, you notice that there are anti-bonding interactions between each of the p orbitals. Okay, but now if you use the block function to generate k equals pi over a, you get the same thing that you got for hydrogen 1s orbitals. As you go from 0 to 1 to 2 to 3 to 4, the sign of the orbital changes from plus to minus to plus to minus to plus. So now, as we change the sign here, this is the plus orbital function. Now we've gone to chi1 where it is minus, and the minus flips the sign of the p orbital. Instead of being the light lobe on the left and the colored lobe on the right, we've got the colored lobe on the left and the white lobe on the right. And now chi2, it's still white and black, left and right. Chi3 again has a minus sign in front of it, so we flip the orbital. We reflect it about the nucleus. And those p orbitals then form bonding interactions in the pi over a case and anti-bonding interactions in the k equals 0 case. So yes, Salvador is asking, why are you depicting the p orbitals horizontally instead of vertically? And this is a good question. You also can depict them vertically if you want. Right now, we're only considering the orbital direction that points along the chain. So we're just looking at the sigma bonding interactions. You could, in principle, line them up vertically and in parallel to one another, and then do the same k equals 0 and k equals pi over a trick where the minus sign inverts the sign of that orbital. Okay, and you're going to get a different result. We're going to do that here in a few slides. But for now, we're just talking about the sigma bonding interaction to illustrate that the k equals 0 solution now actually is the all anti-bonding combination. And k equals pi over a is the all bonding combination. So something happened, right? Before k equals 0 was the all bonding combination, and k equals pi over a was the all anti-bonding combination, and now k equals 0 is the anti-bonding one, and pi over a is the bonding one. And this is a consequence of the symmetry of the component orbital being used to build the wave function. Okay, p orbitals and s orbitals are different. S orbitals are symmetric functions, p orbitals are anti-symmetric functions, and so they have a different nodal relationship and therefore a different kind of a symmetry, and they respond to this block function differently. So let's take a look then at the next slide. Whoops, here we are, where we've plotted the energies of these guys. So the k equals 0 case, as you go from k equals 0 to k equals pi over a, now k equals 0 is the high energy one, and k equals pi over a is the low energy one. And as you go from 0 toward pi over a through all those different values of k, the energy of those wave functions drops off. right at E equals alpha, you're going to pass through a non-bonding molecular orbital until you get to the all bonding case on the right. So actually, here's another typo. K equals 0 should be all antibonding in this case, and K equals pi over A should be all bonding. And you know that because this K equals 0 one has got all these nodes in between and is high in energy. Okay, so this is different than the previous case. The energy goes down as you go from 0 to pi over A, right? In these previous cases here, the energy goes up as you go from 0 to pi over A. Okay, so it's kind of cool that you can see that just by looking in the Brillouin zone here of unique values. You can see how the basis orbital function responds to changes in K by how it changes with energy. Now, if you think back to your densities of states diagrams for a minute, and you take one of these energy versus K, if you take this energy versus K diagram on the left for these p orbitals here, and you do you take the derivative of energy with respect to K, you actually recover the density of states diagram. This is a measure of the number of orbitals in energy and how densely spaced they are. And you get this interesting looking function with two peaks near K equals 0 and near K equals pi over A. And right in the middle, you get a minimum where the slope of E versus K is the largest. And I've plotted on this diagram the Fermi energy here just to kind of help you see how these two things relate to each other. Remember that the band fills up with electrons up to the Fermi energy. And you know, you're used to thinking about that in the case of metals and semiconductors on the right. You can also think about that on this E versus K diagram on the left, right? Those various molecular orbitals fill up until you run out of electrons. If it's a totally filled band, you know, the energy of the Fermi energy might be all the way at the top of the band. If it's a metal, like is depicted here, where the Fermi energy is in the middle of the band, you'll find it at some intermediate value of K. Okay, so the density of states plot, you know, you're used to thinking about these things filling up. E versus K, you can also show how the Fermi energy lands within the band of possible orbital states. But here you're seeing what symmetry, what wave function it is that's filled up. Another thing to be aware of that is quite useful here, or that makes these energy versus K diagrams powerful. You know, imagine if this were a s orbital band instead of a p orbital band, right? I can look at this energy versus K diagram on the left and know that this is a linear combination of antisymmetric functions because it starts off at high energy for K equals 0. An antisymmetric function like a p orbital basis set here with K equals 0, the antisymmetric function is all antibonding, and the highest energy state is at K equals 0. If it were a bunch of hydrogen 1s orbitals, this line would start down here at -2 beta and would go up as you go to the right. You don't see that in a density of states diagram. Density of states has nothing to offer you with respect to what are the component orbitals that make up the band. So an E versus K diagram is pretty darn useful in that sense. It tells you about the symmetry of the orbital involved. It also tells you roughly what the nodal structure of the orbital of the wave function is at the Fermi energy. So those are powerful things. We're going to talk about how those teach you about things like charge transport mobility in a few slides. Okay, so E versus K diagrams are powerful. Knowing about the symmetry of the orbital, knowing about its wavelength tells you about the electron's properties in a way that a density of states diagram really doesn't. And so most physicists, they show both, but the E versus K contains a lot more information, although sometimes harder to look at. All right. So let's take a look at a more interesting example of this to just sort of drive this point home. We're going to do this example of a linear chain of platinums, okay? These are really fun molecules. So this example is this material, tetracyanoplatinate. Okay, tetracyanoplatinate is a salt. It's 2 minus, and it has 2 potassium countercations. And so with 4 cyanide anion ligands and a 2 minus charge overall, you know that the platinum center in that molecule is platinum 2. Platinum starts with 10d electrons. And so platinum 2 has 8 electrons in the platinum's valence shell that are not really participating in bonding much. Now, in potassium tetracyanoplatinate, what you'll find is that this thing packs into chains. It does this really fun thing where all of the platinums stack, and you make a big, long, linear sandwich of platinums where the platinum orbitals are interacting pretty strongly. The spacing in the dipotassium tetracyanoplatinate is really about 3.3 angstroms, which is relatively long. Okay, so there's not a very strong interaction in the pure salt. It's 0.6 angstroms or half an angstrom longer than in platinum metal, and those distances are really probably within the van der Waals contact, but there's not a strong bond there. And this compound is actually sort of a pale yellow solid. It's kind of relatively uninteresting, but it has a tendency to oxidize. Okay, and so anybody that's worked with platinum, especially planar platinum compounds that can stack like this, they have this tendency to oxidize. And when they oxidize, they develop these really deep, beautiful colors. There's this whole class of compounds called platinum blues that develop very strong optical transitions if you just oxidize them a little bit. Okay, so the neutral compound, or I should say the pure dipotassium tetracyanoplatinate, it's an insulator. It's a pale yellow, kind of unremarkable thing. But if you oxidize it a little bit, it changes colors. Okay, so in the solid state, you expose crystals of this stuff to a little bit of bromine vapor or oxygen, they change colors. And if you look at them under a polarizing microscope, you can find that when the crystals and the long axis of the crystals is aligned with the microscope, you end up with this wonderful metallic looking copper sort of a color. If you look at the crystals down the chain, along the chain's axis, they still look pale yellow, but they have this wonderful deep metallic luster when looked at side on. The extinction coefficients are also very different. So a little bit of oxidation really turns on strong transitions and deeply colored optical absorption features. Now, that is a signature of something forming kind of like a metal. If you're working in an organic chemistry lab or doing synthetic chemistry, and you find you make a deep blue or deep green kind of inky solution, while working with some aromatic molecule, for example, that's usually a sign you've made some kind of a radical, which is, a free radical, especially in a conjugated system, tends to develop these dark, deep blue green colors. And those transitions are kind of like the transitions of a metal. It's a sign that there's a free radical in a bunch of orbital states that are closely spaced in energy. All right, so how do you explain that result using the molecular orbital picture, which I've drawn here on the right? So on the right-hand side, I've shown the MO diagram of platinum, and the z-axis, which is not labeled here, I'm going to have to add that. Get you to it that time. So the z-axis here is going to be along the chain. Okay, so what I've shown with the simple MO diagram here, all these different orbital levels, this is the MO structure of just the individual tetracyanoplatinate fragments. So maybe you're a little out of practice here, but if the z-axis is along the chain of platinums, then the x and y axes can point directly at the cyanide ligands. And that makes the dx squared minus y squared orbital on platinum the one that's doing all of the bonding. And the anti-bonding sigma combination here, the empty orbital on platinum, is very high in energy compared to the rest of these guys. So dz squared, which has lobes along the platinum axis, doesn't really interact very strongly with the cyanide ligands. And so it sits down here low in energy. dxz and dyz and dxy also do not interact strongly with the cyanide ligands in a sigma bonding sense, and are also low in energy. They actually do in a pi bonding sense, but that's not really carefully depicted here. The main thing to know about is that the x squared minus y squared is the d orbital that points at the ligands and forms strong sigma bonds, and so the anti-bonding combination of those interactions is this empty function here. You can also think about the p orbitals on platinum and the s orbital on platinum. The x and the y axes point at the cyanides, and so those p orbital functions, they also form bonds with the cyanides, and the empty piece of those gets pushed way up in energy. It's hard to put an electron onto the x or y axis because you've got a cyanide lone pair sitting there. Okay, so those p orbitals are high in energy, and then the s and the pz are sort of down here. Okay, so each one of those tetracyanoplatonates has this sort of molecular orbital structure. If you need a refresher on that, I'm happy to provide one beyond what I've already discussed here in class. Now, if you consider how each of those tetracyanoplatinate fragments interacts along the chain, you end up with a bunch of different bonding possibilities. Okay, so let's first talk about the sigma bonding combination. So along the chain, you have z squared. Z squared is pointing at the neighboring platinums. Okay, and so you can imagine two dz squared orbitals pointing at each other and making sigma bonds. The same is true of dxz and dyz. These are d orbitals that have two lobes that are pointing at each other, but they actually have a node running along that axis. And so really they form pi bonds between each of the platinums, pi bonding interactions. And then the last is the dxy and the dx squared minus y squared. Those guys are sort of also parallel to each other, making a sandwich with all four lobes. Those orbitals make delta interactions. Now, sigma bonding is much stronger. The orbital interaction strength is much greater for two orbitals pointing right at each other. As you add nodes along the internuclear axis, you get pi and then delta. And those nodes and the pi and the delta symmetry lead to weaker interaction strengths. So sigma bonds generally are better than pi bonds, which are better than delta bonds. And so you get different orbital interaction strengths for each one of those basis functions. Pz squared makes up the sigma bonding orbitals. You get a big spread. Pz also makes up sigma bonding interactions and has a large spread. compared to the pi interactions of dxz and dyz, or the delta interactions of dxy, or dx squared minus y squared. So you can see each one of the bands of orbitals that you get has a different band width. Sigma is greater than pi, is greater than delta. So let's take a look at some of these block functions here on the next slide. Here we've taken now solutions for the block function in E versus K sense. I've plotted those solutions over here on the right for the various orbitals. And I've shown you the block functions down below. So let's just start by looking at the orbitals, and then we'll go over to talking about this E versus K diagram. So let's look at dz squared down here on the bottom. You can see dz squared for k equals 0. This is k equals 0. Its solution is just the sum of all of the dz squared orbital basis functions without changing their sign. Okay, so dz squared is a symmetric function, and that means that each one of the interactions for k equals 0 is a bonding interaction. And for pi over a, now of course we change the sign. The first one is plus, the second one is minus, then plus, then minus, then plus. And so you can see that pi over a is a sigma star. Now let's do the xz and the yz orbitals. Now, notice I've drawn parentheses here around dxz and dyz. This is a doubly degenerate set of orbitals, so I've only shown you one. The other one would sort of be pointing in and out of the page, okay? But it's the same as the solution that I've shown here. So you can see now for k equals 0, the nodal structure is the same in each of the d orbitals as you go from 0 to 1 to 2 to 3 to 4. But if you look at the interactions between the d orbitals along this chain, you'll find this is an antibonding interaction. This is an antibonding interaction. So for k equals 0, this pi symmetry orbital, the k equals 0 solution is all antibonding. And then you go to pi over a and you change the sign each time. And you can see you get a bonding interaction, a bonding interaction, a bonding interaction, a bonding interaction. So this is the same as the p orbital basis that we talked about before. K equals 0 is all antibonding. Here's the pz function doing that same thing. The k equals pi over a solution is the all bonding one, the opposite of the dz squared sigma basis. Now let's look at delta. We got delta orbitals here. This is dxy, or dx squared minus y squared, if you like. And you can see that not changing the sign gives you a bonding interaction. These guys are parallel to each other. Just to make sure that I'm going to stop my sharing for 1 second here. You have two orbitals that are parallel to each other in the delta case, okay? In the pi bonding case, you have two lobes pointing at each other like this. In the sigma bonding case, like this. Pi bonding case has got a node running through them. The delta orbitals are parallel. There's actually two nodes that are shared. Right, here's the deltas. These are making a sandwich. And you can see that this k equals 0 solution is all bonding, and the k equals pi over a one now is anti-bonding. So sigma, pi, delta, you just switch. Bonding, anti-bonding, bonding. Okay? So now let's take a look at the E versus K diagram. As you go from 0 to pi over a, the energy varies. The dz squared goes from the all bonding one to the all anti-bonding one. dxz and dyz starts off all anti-bonding and then drops down to all bonding. xy is one of these delta symmetry orbitals, this guy here. So k equals 0 is all bonding, and it goes up to all anti-bonding. Same is true for x squared minus y squared. It's a delta symmetry orbital. Pz is an antisymmetric function, so k equals 0 is all antibonding, and it drops down from all antibonding to all bonding. Okay, so the other thing that you notice here is that the spread, the bandwidth is different. Why is the bandwidth different? Would somebody please comment?
Is it the strength of the overlap between the different orbitals?
Yeah, bandwidth is about orbital overlap, right? And as Vicky said, orbital overlap is greatest for sigma. So the dz squared E versus K function is broader. And the least broad is the delta orbital one, okay? So what about their relative positions in energy, not just the spread, but the ordering? In order to get that part right, you need to know something about the component orbital functions, okay? So I've shown you on this previous slide here how dx squared minus y squared, pzs, px, py, dz squared, etc., how they spread out. This is all about the local bonding within a tetracyanoplatinate unit. Okay, so now, where is the Fermi energy? The Fermi energy in tetracyanoplatinate, you also need to know the orbital occupancy of each of the pieces. So potassium tetracyanoplatinate is a D8 platinum center. Platinum starts with 10 electrons. This is platinum 2 because the tetracyanoplatinate fragment is 2 minus. You have 4 1 minus ligands, so you have to have a platinum 2 plus. So there are 8 d electrons, and that means that the d orbitals are filled all the way up to the top of the dz squared band. Okay, so I've drawn this Fermi energy now positioned over this dz squared, the top of the dz squared band. And so all of these orbital energies are filled, and all of these guys are empty. So what kind of material is potassium tetracyanoplatinate? A semimetal, a metal, or a semiconductor? Anyone? Nobody knows if this is a semiconductor, a metal, or a semimetal? What is the definition of a metal in the context of Fermi energies and band structure? Metal has holes. Partially filled band, I think, is the better way to say that, Avery, but I see what you're driving at, right? A metal is a material that has a partially filled band. And so what that means is that there are orbitals, very, very, very infinitesimally small distances in energy that are empty and filled. And so the electron can hop around from a filled one to an empty one very easily. In a material where all of the orbitals are filled, the electrons can't move. There's nowhere for them to go. You have to populate some empty state that's very different in energy. Okay, so an insulator or a semiconductor tends to not pass electrical current because the bands are filled. And there's a gap here, okay? There is an energy level spacing here above these filled states. dz squared is filled all the way to the top, so we've shown the Fermi energy here. And then the next highest level is this energy spacing up to Pz That is the band gap in this material. All of these orbitals are empty. All of these are filled. So you have a band gap in this material and a Fermi energy that fills this guy all the way to the top. This is a semiconductor because of that gap and because the Fermi energy sits right in that gap. Okay? Is that clear? Anybody want to ask a question about that? So I'm going to just take a second to answer Salvador's question here. Before I answer Salvador's question, I'm going to answer Victoria's. So let's say what is a semi-metal? You know, graphite is a semi-metal, right? We also talked about tin and mercury telluride. These are materials where there is no band gap. People talk about it as a zero band gap semiconductor. They're materials where the empty levels and the filled levels almost touch, or basically do touch in energy. And the Fermi energy is right at the junction between the filled and the empty. So if, let's say, PZ were really strongly interacting and came down all the way here to DZ squared, or let's even a little more fun than that, take tetracyanoplatinate chains and squish them. If you take a crystal of this material and you squish it in an anvil, you can actually force the orbital interactions to become stronger, the bandwidths to become broader, and eventually these two will touch. The broadening will push this one down and push this one up, and eventually they'll touch. And that zero spacing is a case where you get a semi-metal. Okay. Wendy wisely asks, why is the Fermi energy here? We haven't talked about thermal promotion effects. You can assume that this is at 0 degrees Kelvin, and so all of the electrons sit down at the lowest possible levels, and so the Fermi energy sits here at the top of the Z squared band. Okay, so semi-metal would have no band gap. It would have a filled one meeting the empty one right at the junction, right at the Fermi energy. And so Salvador asked, how do you know about the relative spacings of these guys? You really need to know about molecular orbital theory of transition metals to understand how I positioned these, just beginning from one tetracyanoplatinate unit. This is the MO diagram for one tetracyanoplatinate unit, and it arises from the strength of the interactions of the cyanides with the platinum center. And so these energies are E alpha on this diagram. E alpha is right in the middle here. Okay, so dxy, it's E alpha is there, dz squared E alpha is there, xz, yz, E alpha is there, which is the same as what I've drawn here. Okay, dx squared minus y squared, the E alpha is much higher. Whoops. Here's dx squared minus y squared, much higher. PZ, way up here, even higher than that. I should add this to that diagram so you can see the E alpha values for each of those different component orbitals. Yeah, so Avery said, let's say PZ and DZ squared touch. Can you tell if it's a metal or a semi-metal? The definition is a little bit weak. Generally, semi-metals are just thought of as cases where the bands nearly touch or very slightly overlap or precisely touch at the Fermi energy. A metal tends to be a material where the Fermi energy falls in the middle of a big band. If you really squish them together, they would strongly overlap, and you would get a metal. And I think I mentioned last time, if you take hydrogen atoms or hydrogen gas and you put it into an anvil cell and you really pressurize the hell out of it, eventually it turns into a metal like sodium. And at some intermediate pressure, you get a semi-metal. where the bands of orbitals just touch. All right. So now let's do a little bit more complicated example. And this will be a good introduction for next time. So we're going to look at a square lattice of s orbitals. Okay, so we're going to just do a net of s orbitals this time. And this example allows us to see how you have to consider more than just one direction in these kinds of crystals. Okay, so if you have hydrogen orbitals in 2D in this repeating square net, there's two different directions along which waves can propagate. The wave function can propagate or oscillate. Okay, so K has a vector. K is a vector, and it tells you about the directional dependence of the wave function in a solid. So you can describe K in terms of its x and y components if you like. Here's an example molecular orbital of this 4x4 square net of hydrogen 1s functions where kx, this direction, and ky, this direction, are both equal to 0. So when k is 0, it's just a sum of the basis functions in both x and y directions, and you get this totally symmetric combination of s orbitals. Now, in order to describe this, people have taken the unit cell of the crystals of interest. In our case, it's a square unit cell, and they draw them out this way. And they look at unique directions in the crystal and express them as these arrows in this fashion. So for a square lattice, if the vector is 0 in both x and y, that particular combination of x and y is referred to as the gamma point in this diagram. Let's say that the k varies along x. That's referred to as the chi direction. And if both x and y directions, you're varying the function along that dimension, then it's referred to as the m direction. Okay, and so this is a little bit complicated, but we'll clarify in subsequent slides. This is an energy versus momentum diagram that's now plotted in multiple directions. So here, there are various points in this multidimensional space that are plotted. So there's the gamma point here. This is the all bonding combination. This is the gamma point in this two-dimensional space. The M point is pi over A in both x and y. Okay, this is the y direction and the x direction varying from 0 to pi over A, and you'll see this is the all anti-bonding combination. And the x direction is actually the non-bonding case. It's the one where k is varying from 0 to pi over A only in x and not in y. So I think that we are out of time. I'm just going to jump ahead to sort of show you what those wave functions look like for x and m. You can see you get different combinations of s orbitals depending upon which direction you're pointing. Here it's varying only in x and not in y. Here it's varying both in x and y. And you can see this one is all antibonding and this one is not. It's intermediate. Okay, so please take a moment to, if you haven't already started or you're just partially gotten through it, read the Hoffman article. Okay, Hoffman has a really nice presentation of this stuff. These are his figures, actually. We are going to continue talking about that stuff. Okay, so it's going to get fun from here. All right, so I'm going to stop there. Would anybody else like to say anything before next time? I will do my best to get your literature reviews back to you tonight, and give you some material to work from in preparation for the next one. Read the Hoffman article, and I will see you on Tuesday. Best of luck to you all. I hope you're doing okay, and I look forward to spending some more time with you next week.